Okay, testing 1, 2, 3, testing 1, 2, 3. Oh, there it is. Oh. Beautiful. Okay. Muttering, fan noises, everything's recorded just fine. Yes. So, YouTube. Look at that, huh? If at first you can't succeed, stream elsewhere. Central Canada. So anyway, I think the topic is pretty well described in the description, and that is dealing with the NVIDIA, dealing with anything NVIDIA is a struggle at the best of times unless you throw out huge amounts of money. And I do mean ridiculous amounts of money. And all you got to do is take a look at the drivers. Yeah, and I can see that IRC is up, which is good. I can see it. Hey, Marion. The drivers, depending on what you have. NVIDIA is continuously dropping support on stuff. It's sort of like you bought a car, a top of the line car, like 8 years ago. 8 years ago, 9 years ago, top of the line car. As far as the NVIDIA people are concerned, they've got your money and they don't want you driving that car anymore. They don't even want to support you driving that car anymore. In fact, they just want more money. More money. So I think a way to look at this is, actually, let me just do a search here for NVIDIA drivers for Linux. It'll take us to a general purpose page, this, and it'll be a bunch of versions. And there they are. Ooh, let's accept some cookies. I like cookies. Cookies and beer. Yeah, once they have your money, they just want more. And they want it as soon as possible. So, if you take a look at the latest production branch of these drivers, let's just go over here and take a look. The latest production branch is a 535 dot whatever version. Lots and lots of changes and things happening, but there's a supported products list. And you got to take a look at the supported products and go down to, get away from all the gamer stuff. All this GeForce stuff is all just gamer stuff anyway. I'm talking about the computational stuff. Quadro. The Quadro series stuff, that's their top of the line server class computational compute GPU blah blah blah, all singing, all dancing, advertising, marketing, and sales lingo aside. It's supposed to be the top of the line. It's supposed to be the good stuff. And funny enough, they've got a Quadro K2200 on there. That's Kepler, by the way. Kepler series. The M is Maxwell series. Then there's up here to P, Pascal series. And then you keep going up the scale, and eventually you get to Volta, GV. And then past all that, you start getting to Ampere and other stuff, which is really ridiculous. But a lot of the Kepler stuff is being dropped. Specifically, the Kepler stuff that's capable of doing 64-bit mathematics and 64-bit operations. See, what nobody wants to talk about is that almost everything on this page, almost everything in the supported list this page, and that includes, GeForce RTX 3090 and stuff like that people go and spend $3,000 on these things. They can only do 32-bit operations. You try using them to do 64-bit operations, and performance falls out of the sky, collapses. They're barely functional at 64-bit. Now, the whole world switched over to like 64-bit computing somewhere in the late 1990s. I think Sun Microsystems released the 64-bit processor called the UltraSpark. The UltraSpark Spark V9 somewhere in 1996 or 97 on a server called the Sun Ultra 1 or Sun Ultra 1E for enterprise. Whatever the case may be, is it was a 64-bit machine that did 64-bit computing, 64-bit operations, 64-bit opcodes, registers were 64-bit. I mean, it was a 64-bit processor back in 1997. Now, if you go further back to say 1988, 1989, you know, the big hoo-ah was, whoa, we're going to go to 32-bit computing. Well, 32-bit, 1988, 1989, like OS2 in 1988, 1989, 32-bit Windows 3.11, 3.15, or 3.51. Windows 3.51, Windows NT. Just a second. I have a prop. What we have here is, for those of you who recognize it, Windows NT Workstation. Anybody remember that? Windows NT Workstation with support for OpenGL. Yeah. And on top of this, this is version 3.51, Windows NT Workstation 3.51. You could install Microsoft SQL Server. You could do all kinds of interesting stuff with this, and it gets even more crazy because people probably don't remember this, but it was made for platforms, multiple platforms. Some are on here, it says. System requirements, a 386 or higher processor, that's 32-bit, 12 meg of memory. But I do believe that Windows NT was able to run on the DEC Alpha, IBM PowerPC, 32-bit, and on MIPS systems. It was cross-platform. It was a cross-platform operating system, and so was Windows NT 4.0 that came later. It was cross-platform also, but generally only the DEC Alpha, and then x86, and then of course all cross-platform support was dropped, and you couldn't install it on anything except for x86, and it was all 32-bit. Then along came, a little bit later, Windows Vista Business Edition. Windows Vista Business Edition, 64-bit. Not only was Windows Vista, woo, nice, snazzy looking. Look at that, isn't that pretty? Pretty. And in this, there's a 32-bit and a 64-bit installation DVD. I do believe it's a DVD, not a CD-ROM. This disc contains 64-bit software only. The 32-bit one is in there also. Windows Vista. By the time Windows 7 came along, Windows 7 Ultimate, yay, Ultimate, you could run 100% 64-bit. Pretty much everybody was doing everything with 64-bit computing. By the year, what? 2006, 2008, thereabouts. Not with NVIDIA GPUs, you don't. No, 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 no. 9999. NVidia, never removed from the box. Oh no, those have all been installed and run. They're valid licenses. I paid for them. You know, I pay through the nose for a Windows version once every 3 or 4 years, another $350 for the top of the line edition. Although I'd like to have the long-term stable Windows 10, the LTS, long-term stable Windows 10, maybe. But anyway, back on topic. A lot of devices are drop dead here, but what you don't know is most of the devices listed here, like almost all of them, they're only good for 32-bit computation. They can't do anything else. You take a look at a Quadro Pascal P6000. That's a big card. It is a big, big card. The Quadro P6000, you can go to the Tech Power Up website. They'll have specifications on it. This is an expensive card. I don't know what it cost originally, but it's definitely, well, there's the launch price, $6,000 US, this thing, from 2016. But if you look closely at the specifications and go down to its so-called theoretical performance, they talk about 16-bit floating point, 16-bit floating point, 16, which means some of those bits, you got a sign bit, you got some exponent bits, and then you got very little left over for data. And they call that 16-bit floating point. Really fast. 197 gigaflops. Sure. 32-bit. Okay, 32-bit. Now we're at 1988, 1989. 32-bit floating point. Look at this number. 12.6 teraflops. That's 12,600 gigaflops. It's huge. You try to do 64-bit with it, and it collapses down to 394 gigaflops. That's 0.4 teraflops. 0.4. It goes from 12.6 at 32-bit down to 0.4 when you go to 64-bit. Performance collapses out of the sky. 32-bit. This is a 32-bit crunching card. Why would anybody spend $6,000 for a GPU? Anything to do computational, anything with, excuse me, 24 gig of memory in there, and you're basically locked to 32-bit. You try using this for 64-bit anything, performance just falls out of the sky, collapses. Remember that number, $6,000, 0.4 teraflops, 0.4. Let's look up a different card, a Kepler K6000. This is an older card. There it is, the K6000. 12 gig of memory, 384-bit bus width, you know, so we're in the vicinity. 2,880 cores, CUDA cores. This card was manufactured way back in 2013, 10 years ago, and it cost a little over $5,000 at the time. Again, big money, top of the line. This is a bone cruncher of a compute card. Take a look at the so-called performance. 32-bit, 5.2 teraflops. 64-bit, 1.7 teraflops. This thing, manufactured years previous to the Pascal, is massively more powerful. What happened? Somewhere between the year 2013 and the year 2016, NVIDIA said, we're going to brain damage all of our cards. We're going to make all of our GPU cards, all of them, 32-bit capable only. Unless you want to spend $10,000 plus. I kid you not. You go look at the performance of just about every single GPU sold by NVIDIA, and they are really great at 32-bit, 1988. No problem, they do that. The moment you want to do 64-bit basic run-of-the-mill mathematics and stuff that you can do on any machine made in the last 20 years, and they collapse. They collapse right out of the sky. It gets worse. It gets worse. But wait, there's more. They also have what they call performance libraries. The NVIDIA Performance Package, or NVIDIA Performance Primitives and stuff. The NVIDIA NPP, NVIDIA Performance Package, Performance Primitives, lots and lots of libraries and stuff. You take a look at this stuff for image processing, Fourier transforms, all kinds of stuff. And you'll notice they're all 32-bit. 32-bit floating point, complex, the 32-bit floating point squared magnitude. We're talking about Fourier transform stuff. A set of Fourier transform functions available in the library, and they're all 32-bit. They're 32-bit. You won't find anything in this so-called performance package that can do anything 64-bit. Go looking. You won't find it. There's an endless supply of 32-bit stuff, but you won't get 64-bit stuff. Maybe they keep that in the back pocket someplace for other big corporations willing to spend the money. I don't know, but it's certainly not available to the average user. All right, let's get back to the problem at hand, which is drivers. Drivers. The latest production branch, if you take a look at it, it does not support anything from the Kepler series capable of doing 64-bit. In fact, nothing on that list. Nothing except for these two at the front of the list. The GV100 and the GP100, they're both fully 64-bit ready, and they are thrashing magnificent, powerful throughput cards. 64-bit. And those things will cost you $6,000, $8,000, $10,000 each. Good luck. Good luck. A GP100 these days, maybe, if you're lucky, you can pick one up used. $2,500, maybe $3,000, something like that. And it'll probably work for years and years because it's pretty much top of the line. There's the GV100 and the GP100. Those are really the top of the line, and based on the Volta GV100 architecture, design, processor, chip, whatever, is also a thing called the NVIDIA Titan V, right there. The NVIDIA Titan V is also a thrashing, powerful card. Massively expensive. Everything else, there's Panku. Everything else, 32-bit. They basically want to funnel you and force you into coughing up $10,000. And anything else, forget it. Just go play games. Just go be a gamer. Go play games. 32 bits is fine to go play games. Play games all day long. But if you want to do actual computing, computational level stuff, nah. You got to cough up the money. And it'll only work for now. Who knows when they drop support, and who knows what else is going to stop working. But wait, there's more. There's a beta version, more stuff dropped. And then there's a legacy version, the 470 right here, the legacy version. That driver. And this driver, it gets the occasional update. There it is, May 30th of this year. That's pretty good. And this thing supports a ton of stuff. You go down to the Quadro line, And there's a big pile of stuff in the Quadro series. This thing supports the K6000. So full 64-bit support on the K6000. And you still have your GB100, your GP100, and you got your NVIDIA Titan V. They're all in there. As well as a pile of the gamer stuff, 32-bit stuff, right? If you want to play games, have fun, whatever. But if you want to do anything computational, good luck, buddy. But wait, hold on. 470-182-03, that's this year, March 30th. March, April, May, June. It's like 2.5 months ago. This is very up to date, isn't it? Okay. So then comes the question of, what about if you're on Linux? Stable Linux is version 6.3.8. There's a long-term stable at 6.1.3.4, and there's some weird thing in the middle which is called end of life. 6.2.16 for some strange reason. I haven't figured that one out myself. Maybe somebody can explain why that's end of life. But 6.3.8 is stable. And over here on this machine, it's running 6.3.8. This machine runs 6.3.8, the latest Linux kernel, and the reason being is I built it myself. Of course. There's even a compiler, GCC 13.10. I built that myself too. Test reports have been filed and everything. It's a solid compiler. It's got magnificent test results. The test results have been filed to the public. Alrighty. It does math. It does all kinds of stuff. And funny enough, in this case, this is 128-bit or, big deal. It's a long double floating point number. The correct floating point representation for pi is that in hexadecimal. And this machine produces the exact same bit-for-bit perfect representation, but it can only do it using a library called libquadmath, because x86 hardware can't do this. x86 hardware can't do floating point math beyond, now once you get past 64 bits and you try to go a little bit further, you end up in the desperate world of, you get some kind of a hack. Intel came up with a hack, which is called the 80-bit or 10-byte floating point representation. All I can say is, you don't get this unless you use a math library. Actual hardware cannot do it. Funny enough, we go over to this machine, which is an old SPARC 64. This is NetBSD 9.3 running on SPARC 64. GCC version 10.4, whatever. The machine is big endian, not little endian, big endian, which means the memory representation, when you look at it in memory, kind of looks normal to a human being. Most machines these days are little endian. In any case, it uses a long double, 16 bytes long. And it also has a perfect representation right out of memory. But guess what? This machine, it handles perfect 16-byte, 128-bit floating point, and it does 64-bit floating point, 100% in hardware. It does it all just fine. But it has to use emulation. It has to use emulation math calls to handle the 128-bit stuff. It doesn't do it natively in the hardware. Let's go to another machine. This is Esther. This is on FreeBSD 13.2, but this is a i386 32-bit machine. As a matter of fact, this machine is right there on the wall. It's a motherboard nailed to the wall. Hard drive's hanging underneath it, all strapped up and tied to the wall. Runs just fine. FreeBSD, right there on the wall. It's got a cooling fan and everything, and a speaker. In any case, it thinks the size of a long double is 12 bytes. Not a lot of consistency going on here. Why does it say 12 bytes? The correct representation, again, doesn't change, but this machine thinks that pi is this. And if you take a close look at it, the first 2 bytes are 0. Really, you're only getting these bytes. This is a 10-byte Intel hack floating point representation for a long double precision floating point number. It can't do anything else. You only get 10 bytes, not 16. But it uses 12 bytes of memory to store the data. Why? 32-bit. It's a 32-bit machine. You allocate in chunks of 32 bits at a time. 32 bits, another 32 bits, and another 32 bits. That's the best way to represent 10 bytes in memory in a 32-bit machine. It's aligned on 32 bits. You get 2 bytes wasted. And you get a value for pi, which is wrong. I mean, it's close. You know, it's close. 3.14159265358979, etc. 3238, and then it all falls off right about there. I mean, it's, you know, it's not bad. It's in the vicinity, but boy, oh boy, it's not even close to this. It's way wrong by a lot of digits. That's a 32-bit machine. That's what you're going to get when you pay for your $6,000 GPU card from NVIDIA. You're going to get 32-bit mathematics, and you're not going to get this representation. You're only going to get, if you're lucky, you get 32 bits floating point. No, you get 32-bit floating point. That's what you get. You can try doing 64-bit. Good luck. Here's NetBSD again on an AMD 64 machine. Again, libquad math. Using a library, it's able to give you correct result, and it gives you a value which is pretty good. All those digits are correct. If you want, you can round up that 7 to an 8, and it matches. You get about anywhere from 32 to 34 digits correct. Most of the time. That's pretty good, using libquad math. Again, a library. The hardware can't do it. But wait, it gets more silly. ARM. This is 32-bit ARM. This is what you're going to get with the NVIDIA stuff. With the NVIDIA stuff, it says a long double is 8 bytes. 8 times 8, that's 64 bits. Are you going to get 64 bits? Nah. This is actually beyond what an NVIDIA GPU can do. NVIDIA GPU, well, it might be able to do 64 bits, but it's going to like completely collapse in terms of performance. It's horrible. For $6,000, I'd be pretty ticked off. This machine, the best it can do is give you 64 bits, but at least it does that, and it does it correctly. And that's on 32-bit ARM. FreeBSD, 64-bit on AMD 64 using LLVM Clang. Again, 16-byte long double. That's nice, 16 bytes, that sounds right. Until you take a look in memory at what it thinks pi is. And look at this. 10 bytes of data. 10 bytes of data again. And now you get 1, 2, 3, 4, 5, 6. 6 bytes of nothing. Nothing. It uses 16 bytes of memory to give you 10 bytes of data. That's not even close to the 113 bits of data that you should be getting out of a proper long double. But it will do 64 bits, no problem. This is AMD 64. 64-bit math, double precision, no problem. You're never going to see this out of NVIDIA. No. Not if you spend $6,000, even $10,000, you can't get this. IBM Power 9, very big money. And this is very confusing because this machine is perfectly capable of doing 100% everything in hardware. It will do in hardware 128-bit floating point mathematics. No emulation, no libraries, except when you put in any modern top-of-the-line Linux, you find out glibc doesn't understand the 128-bit standard floating point, and you can't do a printf, and most of your math operations are just a disaster unless you start doing some interesting hokey stuff and possibly some assembly language to use the machine. And again, you end up being stuck with libquad math on a machine that does 100% hardware. The message is, it's complicated. The situation is complicated and convoluted. Tell you what, let's go back over here to this machine. This is Titan. And on this machine, oh, that's interesting. There we go. It has an NVidia K6000 and an NVIDIA GP100. So there's two GPUs in this machine. To support the GP100, I can use just about any driver I want. That's top of the line stuff. The only thing beyond the GP100 is the GV100, and then you get into server data center stuff like the Ampere. Those are $30,000, $40,000, $50,000 each, those cards. They're strictly only in server platforms, and I don't know, I've never seen one. They exist. In any case, the K6000 right there, that does 1.7 teraflops. Floating point thrashing, no problem. At 64 bits, provided you've got the right driver. Oops. NVIDIA-SMI has failed because it couldn't communicate with the NVIDIA driver. There's no NVIDIA driver in this. If we take a look in clock modules, you'll sort. We have all kinds of modules and loads of goodness and all kinds of good stuff. It's in there. Intel this and support for the 10 gigabit. This thing's running 10 gigabit iSCSI using jumbo frames, if anybody knows what that is. I set it all up. In any case, there's nothing in there for NVIDIA. Nothing. There's your NVMe, some other stuff, but nothing for NVIDIA. No driver. Nope. Well, why don't I just install that? I think it'd be a good idea to just install it. Give it a try. Right about now, because it's been 30 minutes of me venting, going blah, 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 blah. Somebody somewhere is going to say, show me something! Right? Right about now is a good time to go get a beer. I'm going to become root. I am now root, or brute. Go into USR, local, build. Yeah, that's Esther. That's Esther. It's hooked up through IRC, such if anybody wants to make music and sounds and things, then Esther does that. It also is a way that other people can notify me, hey, I'm trying to get your attention, and all of a sudden Esther starts making noises. I'm like, someone's trying to get my attention, and so I pay attention. Here we are, NVIDIA, different Linux versions. I've been here before messing with this, and I've got a README file that tells me what to do and whatnot. Just want to point out, I've had great success with Linux 6.2.10, but for some obscure reason, anything 6.2 is end of life. Well, I don't know why. 6.2, end of life. But I know I've had great success with it. I do know it's 6.3 and the 6.4, which is a release candidate stuff, total fail. Let me demonstrate. 60-second pause, everybody. Trust me, you're going to need a beer. Alrighty then. Okay. Oh, and I just want to point out, I'm sponsored by nobody. There's no advertisements, nothing. There's a link in the description. Anybody wants to throw in some beer money, that's great. There's a PayPal link there. That's it. One moment, please. One does not go into NVIDIA driver land without a beer. By the way, this is Innocent Gun. There we go. That's a good looking pour. This is Innocent Gun here. Perfectly reasonable beer for dealing with NVIDIA drivers. Alrighty. Oh, let's not even talk about what Red Hat ships. Alrighty. So currently we are on 6.3.8, which if I was to check, clock version, you'll see it's 638 built by me with GCC built by me on June the 14th. Well, today's the 16th, so, I do get things done. Using binutils 2.40, which, by the way, are also built by me. And this is a symmetrical multiprocessing machine, which means it's capable of managing multiple simultaneous processors. I'm not too sure how to get the specifics of the machine, but if I do neo fetch, which is really kind of cute, it should come back and say it is Dev 1 Linux Chimera on a Stink Station P910. We've got 660 some odd packages installed. That's not too much for Linux. Intel Xeon. It says there's 40 of them at 3.4 gigahertz. Really, it's a dual socket 10 core, but there's hyper-threading, so 10 plus 10 is 20. You get that weird Intel hyper-threading going, and it looks like it's 40 cores. There's your NVIDIA Quadro K6000, the GP100, and there's some memory. It's got some memory in it, and that's all, because it's a Xeon, it's all ECC, LR DIMMs, it's a good machine. Then there's half a terabyte of memory. So, yeah, it's a machine I can use for stuff. Now, 638. So I'm going to make a directory here called Linux-6.3.8 dash Gen Unix. And by the way, Gen Unix is actually the name of the kernel that used to be in Solaris, for those of you who can remember the days of Solaris. Anyway, I named it. Cheers. Now, there's a README file. Oh, one other thing. This kernel uses signed modules. So every module that's loaded is signed using a public-private key pair that I created myself, because I built the whole kernel myself. All the modules are being signed by that key, or they're not accepted. The kernel will not accept or load a module that has not been signed with the correct key. That's important. It just puts in an extra step in here. So I have a README file from when I did this in 6.3.1, which says, do this madness, where I have to identify the kernel key, but it's going to be for 6.3.8. I also have a sign file. Funny thing, if you go digging around inside the Linux kernel, it talks about scripts and things. If we do take a look at Linux 6.3.8, there it is. That's the sources to Linux 6.3.8. There's a directory, funny enough, called scripts. You go looking around in there, you've got some Perl stuff, you've got stuff written in C, you've got stuff which is assembly. There's various different things in there for doing various different things, scripts and stuff. One of them is sign file, right there. See that? That thing is written in C. If you go digging around in here, you'll see 2014 Red Hat, Intel, Hewlett Packard Corporation, and then some really good guys. I mean, David Woodhouse, man, he's been around a long, long time, does a lot of cool stuff with IBM Power, PowerPC stuff. Yeah, David Woodhouse has been around for a long time. He does great work. In any case, if you go digging around in here, eventually you'll figure out that it's all about how to sign a file. It talks about private keys. You've got this engine stuff going on, the new bio calls and whatnot from OpenSSL. That's a whole other discussion. It's a whole other discussion. I realize this is going to be baffling to some people, but what's important is there is a binary file right here. Here it is. Now that binary does things. Specifically, it allows you to sign another file with a public-private key pair such that it can then be accepted by the kernel. You have to do that with modules and such. Now, before we go too much further, this is the NVidia driver. 470.182-03. Let me just check. Let's just see here. 470.182-03. Yep, that's the driver I need. So I need to extract this thing. Because right now that's just like a big file. And I do believe there's a way to just, extract that thing. I believe it's called -- extract only or something like that. Oftentimes what I do is I just look at the file, because the beginnings of this file is all just a script, and then there's a pile of binary stuff. Give it a moment. It's big, but there's command line options and whatnot. It's not the best documented, but at least you can look at it and find the extract only, because that's what we need to do. We need to extract the driver pack to get access to the source code. Oh, good luck, by the way, because a lot of the source code from NVIDIA is proprietary blobs. And you're not supposed to reverse engineer that stuff. Don't go looking. Don't even try. Extract only. Go. And it unpacks. Take a sip of beer. La 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 la. Done. Let's take a look. There it is. We take a look in there. Now we're inside the extracted driver pack location. There's all kinds of stuff in here. Loads and loads of goodness. And some of this stuff, there's man pages and stuff that you can read. There is. You can see there's a .1, like NVIDIA persistent D daemon, this .1. That's actually a man page. NVIDIA settings, NVIDIA SMI, that kind of stuff. There are some man pages in there that you could read if you like, make the effort. Oh, supported GPUs. That's interesting. I don't believe I've ever looked in there. Oh, it's a JSON file. Isn't that wonderful? I have never looked at this, but it's going to be the same as what's posted on the website. I'm not surprised if it actually reads out of this JSON. Oh, I don't feel like going through this. Yeah, that's nice. That's nice. Tesla T10 processor, GeForce this, blah, 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 blah. Anyway, what I need to do is take a look at the README file. This README file, I wrote it because I've done this over and over and over again. I've been through this so many times that now I pour a beer every time. Every time. The NVIDIA installer, well, let's just see, do we have that? Let's see, NVIDIA installer. Yep, there it is. It's executable, and I suspect that this is a script. No, it's a compiled executable. The NVIDIA installer is itself an executable. Don't go looking for the source code. You won't find it. Don't try to like reverse engineer this. Let's go find the kernel key. We need a module signing public and secret, public-private key pair, right? So in this case, it's going to be 638, and it's going to be that key right there. There it is. In that key, that one PEM file. Anybody remember what PEM stands for? Portable Email Manifest or something like that. We also do SHA-512 as the hash, and we need the sign file. That sign file we've already looked at. It's a binary, but it's going to be for 638. I've been here before in 631. Here we go. All right, let's do it. NVIDIA installer, the -S simply needs to be silent. Don't tell me anything unless I need to know. I've already read the man page on this. It's loads of fun, trust me. Module signing key, blah, 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 638. And then I can just copy and paste this, do a continuation character at the end. That's the public key. Private key is actually, it's all in the same file. I'll do the same thing. 638, blah, 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 blah. Do that. I hope you can see this. It should be pretty clear. We are doing SHA-512 as the hash for the signature. SHA-512 part of the FIPS. Anybody know what the FIPS document was? I've forgotten it, The digital hash signing standard document from NIST, National Institute of Science and Technology, from out of the States, which is underneath Homeland Security, what a surprise. And then we need the sign file, which is going to be all of this, 638. And again, script sign file, and just hit enter and let it work. It should just work, right? Let's watch. Uh-oh, CC version mismatch. That's interesting. So it's complaining about the compiler. That's okay. Uh-oh, an error occurred. An error occurred while performing the step building the kernel modules. Oh boy. This file is always fun. An error occurred while performing the step checking to see whether the NVIDIA kernel module was successfully built. Well, it wasn't successfully built. The NVIDIA kernel module was not created. Installation has failed. Failed. And you wonder why I pour a beer first. I bet you it's in this file. This file will tell us everything, right? What is it, 20 lines long? 994 lines. Easy. Let's just read it. We'll just dump it out. Just take a look at it. Whoo, baby. Lots of goodness. Ooh, compile, 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 compiling. We're compiling, and then we're not. This is a warning about an unused variable. I don't really care about a warning about an unused variable. Warning, unused. I'm okay with warnings about unused variables. It's just something goes wrong up here. Error. Assignment of read-only member VM flags. Uh-oh. We got a problem with the management of virtual memory pages. I have a sneaky feeling that this structure doesn't really exist anymore. There's problems. Now, I'm going to try to keep this quick. I notified, or at least I posted this stuff to NVIDIA forums and whatnot months ago. Other people hit the same thing. You go get a stable kernel release for Linux, right? There it is, stable, 6.3.8. Try using it. NVIDIA drivers, good luck. In nomine Patris, Spiritus Glorious, good luck. Get a beer. It's not going to work. But other people have hit this also. And bug reports have been filed. This is Legacy 3.4.0 stuff right here from 16th of May. People are running into problems. There's bug reports on it. Most importantly to me is that other people have also run into this. 4.7.0 Fix Linux 6.3 patch. Patch. Yes. From 25th of February of this year, and this would have been, this is 6.3 RC1. This is back a release candidate. When 6.3 was a release candidate, now it's stable. Oh, this might actually work. So I'm going to glance at it, but really, I want the raw patch file. And I'm terrible with GitHub. There's got to be like a little button here that says raw. Click on raw. That's what I'm looking for. Right there. So I'm going to take this patch, the whole 9 yards, and I'm going to drop that thing into NVIDIA 4.7.0.patch. We'll do that. Bada bing, baby. There you go. Now, what I'm interested in is maybe I could do this manually piece by piece because it's not that big a patch. It's just a few things. It looks like we've got a header file, yeah, memory, non-volatile memory map stuff, yes, okay. So, why don't we handle this line by line? Do it manually. Did I mention you should probably get a beer? Line 1988 onwards. Inline, void, non-volatile mutex destroy. Mutex, mutual exclusion lock type stuff, you know, threads and such. Okay. Does that file exist? No, it doesn't exist. What a surprise. By the way, this is water. Gotta love the Grolsch bottle. Okay. So where's that file located? NVlinux.h. Huh. Because if it doesn't exist, then this is all overdone. Oh, there it is. Kernel common. All right. I just had to locate it. I think what I'm going to do is consider this to be a failure. So this is a failure. Can we agree? It's a failure. Nuke it. Nuke it out of orbit. It's the only way to be sure. The only way to be sure. Just nuke it out of orbit. Okay? And then re-extract fresh code. So we go back here and we re-extract with a, what was it? Dash extract only? Extract only. I think that works. Blah, blah, blah. And I'm going to do this line by line, piece by piece, because I want to take a look at it, to be completely honest. I don't know if this is going to work. Who knows, right? Anyway, so one more time to feeling. There it is. So we need, well, I want to back it up. That's the original. And what I'm going to do is use the power of Vim. The power of Vim compels you. Yeah, right. Let's see. I think what I want to do, since I'm going to take this patch piece by piece and line by line, it looks to me like we're not deleting anything. Looks like line 1988 onwards, we're dropping in totally new stuff before we get to the underscore NV underscore Linux underscore H at line 1988. So why don't we do that? Yeah, let's do that. Line 1988, new text destroy, a lot of big gap there. Isn't that funny? Just a second here. Let me go up here and take a look at this again. Just eyeball. All right. You know, I'm with you. I know we're not getting any colors or anything. Oh well, I can live with it. Let's take out the plus signs, bing. I don't like that kind of comment. I'm going to change that, by the way. And we don't need a blank line there. And we don't need this blank line. And I don't, that's not even worried about that. This I'm going to change because me. And I'm going to make it into a split. So I'm going to take this down to here. Like that. Okay, static inline void, You know what? Here. Is that consistent? No, that's not consistent with their format. So I'll stick with their format. 2, 3, 4. They're using spaces from the tabs. Let's see. Yeah, spaces, not tabs. Okay. That's same. Here's the end if. Okay, so if Linux version code is less than this, then we do that. And that's the only change in that file, I think. Is that the only change in that file? Let's go take a look at that patch. Patch. Bork. Okay. NVIDIA DRM gem user memory is next up for the hit list. Okay, we're done here. Let's go find this thing. .c or .h? Got a header file? Anybody know? No. See, there it is. Let's back it up. Bing. .org original. And just out of curiosity, what's my terminal set to? Yeah, external. Isn't that interesting? I guess we're just not going to get any color today. Okay. Let me go take a look and see what do we got here. So we're past that. Now we're looking at Line 35, we're throwing in a header. Line 92, etc. So we'll just chuck this in under NVidia. Okay, that's in line 35, 6, 7, 8, 9. So take it one line at a time. Line 35, bing, 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 bing. Right there. Chuck that in. Looks pretty small, actually, you know. Oh, they were nuking some stuff. Yeah. This structure's changed. Something's changed here. Now let's go to line 92 and nuke those 3 lines out and then drop these in. Because it looks to me like we're doing, instead of doing an AND equals and then not VM underscore PFN map, it looks like there's a VM underscore flags clear. Oh, new calls. So we clear the flag that way. As opposed to this AND equals not logic. We're doing VM underscore flags underscore clear for the VMA struck. Okay, I'm all right with that. Let's do that. Line 92, right? It's actually line 93 now because, you know, I've already dumped in some stuff. And there they are. Thing of beauty. Let me knock these in and nuke these out. That was easy. Ta-da. Blank line. I don't need that blank line there. Anything else I have to worry about in that file? Let's take a look. No, we're done here. We're done here. We're moving on to the OVM. Sorry, UVM. User Virtual Memory Management. And that's like a one-line change. Look at this, one line. Yeah, VM flag set. We're doing calls instead of this or equals this or. We're doing, yeah, the same or is still in there. It's just now we're doing VM flag set line 812 of that file. Okay, we're done. Anybody following along? I hope someone's following along. If I do anything crazy wrong, let me know. I can only hope someone's paying attention. I'm just winging it. EVM.c. Thing of beauty. Back it up, because I do that. Whoa, 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 Batman. That was a beer click. Okay. And we're doing, what are we doing here? One line, right there. Line 812. Hit me, baby. One time. One time. That's not line 812. Oh, yes, it is. That'll do. That'll do. Let's do that. And nuke that. I think that's the only change we're doing here. Okay. Wow, that's it. That's it. This is not exactly like splitting atoms, you know? All right, we're out of there. Moving on. That's done. NV memory map C. Sure. Back it up. By now it's getting boring, right? I know someone would say, why are you doing this manually? Just apply the patch. Because I want to look at the code. You know? Duh. Alright, what are we doing here? Looks a little bit more involved. Yeah. Okay, so VM flag set. So anywhere we're doing this VMA struck, we're not doing it that way anymore. Things change. It seems pretty clear to me. Okay, let's go to line 447, 8, 9, 10, 450. Let's go to line 450. Let's go there. Bang on, baby. Right there. Done. Nailed it. Okay. Then we need line 590. Let's say 603. Feels like a 603 to me. Anybody? Anybody? Line 603. Nope. I'm in the vicinity. But Not quite. VMA underscore VM flags. This is IO PFN map don't expand, which is IO locked in reserved. No, I'm in the wrong place. IO 15 don't expand. No, that's it. That's it right there. Okay, if we hit it, 96, 97, 98, 99, 600. Line 601. Line 599. Whatever. We're in the vicinity. This is why I do stuff manually. Sometimes things don't quite line up. Okay, line 663, we've got these. Whoa! 663, so 666. 666, NVidia. Whoa. Yeah, nailed it. Actually, you know what? Let's do this. Check it. Same flags, same logic. Just we're using those calls instead. Okay, I'll do it that way. All right, so that's done. What do we let? Well, that's it. We've got lines. If prot and NV protect writable. If prot and then prot. This doesn't look right. Something's not right here. That can't be right. This needs to be. That structure can't be right. Hold on a second. No, that's left. So this is untouched and that's struck. But these flags are handled this way now. Right and they right. Well, someone else has been here before me. Feels a little funny. Feels a little strange. Sometimes I wonder who wrote the patch for me. Yeah, okay. All right, that looks good. I think we're done here. NV map. Okay. So let me take a look at this patch one more time, just to eyeball it. You know, just yeah. Did I miss anything? Anybody? Anybody? Bueller? DRM user memory event mmap. So 4 files changed. So those are the 4 files. See. Okay, so there's the header. It's not like it's alphabetical or what. I don't know. Yeah, that looks right. And yep. Okay. So the theory is we've applied the patch. Phasers on stun, and may the force be with you. Let's give it a try. And yes, I was mixing metaphors. All right. Let's take a look at that README file again because I'm dumb. You know, I need this stuff spelled out for me. So let's do it again. Patched. So again, this is going to be 638. I hope this works. But then again, it doesn't really work. We don't know, right? Gonna have to do some who knows? Let's just see what happens. SHA 512, and again 638, and that is the sign file. Punch it, Chewy. Yeah. Ignoring the CC version mismatch. That's nice. That's easy enough to fix. But I don't really care. That's fine. 32-bit, we don't care. And we don't care about that either. What we have here is a success. Maybe. So let me just hit the README with enthusiasm. Dump that in there. Go in here. Apply the patch as seen at. Give me a link. That way I can get back to this guy and say, hey man, guess what? Works! But then again, who knows, right? There's that. Files affected, touched, or otherwise given love to was here. Hey. Whoop. Okay, done. Proc modules. Grep outside a tree. Nothing. There they are. NVIDIA, DRM, mode set, NVIDIA driver. Signed. Loaded. Just, excuse me, lib, modules. Hey, 6.3.8, are you there? Thank you. Kernel, drivers, video. There it is. June 16th, 1837 hours. 2 minutes ago. Interesting. 1611, VGA State. Golly gee whiz, Batman. How did that happen? Local, build, NVIDIA. So, 6.3.8. Don't mind the beeping. The beeping's in there on purpose. It's to tell me that I'm being an idiot. Good to know. That's the README. Hey. Ended up in file 1. I see it. Okay. Let's see if it works. There they are. There's the Quadro K6000. Goes up to 225 watts. There's the GP100. Goes to 235 watts. Sitting around. Fans at 26%, 34%, whatever, 41, 48 degrees Celsius. Well, the GP100's at 48 degrees Celsius. It's on the top of the machine. Heat rises. You know, it's above the processor sockets. It's a little bit warmer. Let's test it. Now, you may be wondering, this is like, I'm coming to the end of this process because it worked. So, quick test. What I'm going to do, I'm going to use that. I'm going to build a test mule, optimized. So So I'm going to do a test mule using this GCC that I built. This, like that. Let's take a look at common. This is all my code. Yeah, okay. Let's see what happens. Bada bing. Okay. And let me check my output. I want a data set test. This is a test mule. Basically, it does a lot of numeric number thrashing and generates a fractal, Mandelbrot fractal type thing, nothing fascinating. So out of my output, I've tested this on all kinds of systems, including RISC-V. So let me run this. Should be pretty quick. Let me check my temp directory. There's some junk in there already. I'm going to remove that trash. Run this. This will be quick. And I'm just going to hit the center of the grid. Now there's no GPU stuff here. This is just, this is just pure CPU thrashing. Okay? Looks right to me. Dump it. Okay, so all the data that was just computed, this is 1024 by 1024, so that's 1,048,576 data points. Each data point is a complex value, real and imaginary, as well as a altitude value based on the Mandelbrot fractal computation. It's not rocket science, So that produces an output data file right there. Let me just get the first 96 bytes of that. I'm only interested in looking at the signature because I know it off the top of my head. It looks right to me. And then we got data. The data pack is going to be 64 byte values, and then you got your 32-bit value, and then it switches over to 64. Yeah, this looks good. Yeah, this looks good. Okay. Open SSL digest, DGST SHA 256-R. Let me get a signature on it. There's a signature. I don't think this is unique. I think, yeah, that looks correct. That looks correct. If I go grepping for that signature in my output directory, wherever, yeah, so that's correct. Doesn't matter where you do it. This is Xeon, Spark, IBM Power 9, this is PPC 64, big endian IBM Power, Linux on Spark, Linux on Xeon, Core i7, ARM, and wherever you do it, doesn't matter, exact same numbers. That's good code, right? That's good code. Anytime you write code that you can run on all kinds of different systems, on Linux, on FreeBSD, different operating systems, different architectures, ARM, 32-bit, 64-bit, big endian, little endian, RISC-V, it just works. Exact same data every single time. Okay, so what I'm going to do is I'm going to create a new output file here, which is kind of repetitive. I'm just going to say, this is optimized. And I want to point out the computation time here. This is really important to take note of how long it took to compute all that. All right? This is something I've done over and over, Okay. There we go. So, if I go grepping, now there's Linux Xeon optimized. I just put it in there. It's an output file. But what's important is timestamp. There's a timestamp up here that says, right there, 1.515, etc., times 10 to the power of 1, that's 15. 15.15, 15.16 seconds. So to do that computation, 1,040,576 computation pixel things using the Mandelbrot stuff and a lot of math. I mean, a lot of thrashing math. 15.15 seconds. Are you sitting down? I hope you're sitting down. Because that was called data set 2. And that's my input data right there. La 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 la. La da da da. Dee dee. Exact same computation, but now I do it using NVidia CUDA code. So in here, I just want to check to make sure, because I think I did this, yeah, data set 2. I tested this on another machine. So that data, I think that data looks correct. Let me just verify the numbers. So bailout 32,768. We got a huge number. Yep, that's correct. 098 is correct. The 9477 is correct. And we're doing 1024 by 1024 pixels. Right. So that's a million. Okay. Yeah, no beard. A woman happened. I have a compile script that does all the hard work for me. It's not worth looking at. So now I'm going to get some warnings about some variables that I set but didn't use. I don't care. It's now going to run with the profiler. Okay, so the compile worked, it ran, and it dumped out a file. File dump is done. Notice the execution time. Pay attention, because we got an output file, and there it is. There's the output file, right there. With the previous one, which means, this is today, both files have the exact same SHA-256 hash signature. That means exact same data. Exact same data, exact same output, exact same computation, except a GPU, NVIDIA Quadro GPU, wide open, unrestrained, does it in 23 milliseconds. 23 milliseconds. Moving the memory around took, that's about a millisecond there, average each. So let's get another 2 milliseconds. So let's get another 2 milliseconds. This is 835 microseconds. Let's call that another milliseconds. Let's say 23, 24, 25, 26. All in 27 milliseconds. So 27 milliseconds on an NVIDIA GPU Quadro with full capability to do the exact same computation that a top-of-the-line machine, Xeon, 3.4 gigahertz, whatever, needs 15 seconds to do the same computation. There's some overhead on the X Windows stuff, right? There's some overhead on the X Windows stuff, but come on. 15 seconds, even if we took around, get rid of all the X Windows X11 stuff, you're still looking at seconds as opposed to milliseconds. In fact, that entire computation was done fast enough. The whole thing is over and done with in 30 milliseconds. So let's suppose hypothetically you want to do animation, computation, and you want to be able to do 30 frames per second. 30 frames per second, 1 divided by 3, right? You're looking at about 33 or 30 milliseconds that you need to produce every frame. You got another few milliseconds to get it on the screen. That's another challenge. Anyway, I think we're done here. I think we're done here. I'm going to have to get back to the guy who wrote the patch and let him know. Stable 638, there it is. And I've got NVidia CUDA, NVCC, right? That's working. I'm happy. We're done here. Thanks for listening. Games want 120 frames per second. Well, games can operate at 32-bit, right? Who cares? Gamers. Whatever. We're done here. Thanks for listening. And that's how that's done.